Let's talk about the definite integral for a vector function. Just assume we have a vector function that has three scalar component functions, and we know that f, g, and h are all integrable over the interval a, b. Then, the definite integral of the vector function from a to b dt is equal to the vector we get by taking the definite integral of all three component functions. Well, this is great news. This is the same idea we've had throughout this section. Whenever we've needed to do calculus on a vector function, we simply do exactly what we already knew how to do from Calc 1, but on the scalar component functions. And this is no different. So let's do an example. We've been asked to evaluate this vector function's definite integral. So the definite integral from 0 to pi thirds of secant tangent in the I component plus secant squared t in the j component, and then 2 sine t cosine t in the k component. Well, I recognize easily antiderivatives for the first two. This last one, the k component, well, let's just do a little simplification before we get started. Two sine t cosine t is a double angle formula for sine. So that's really just sine of 2t in the k component. So now let's just find some antiderivatives and then see if we can evaluate the definite integral. The antiderivative of secant tangent is secant. And we'll need to evaluate that from 0 to pi thirds, and that will give us our I component. The antiderivative of secant squared is tangent, evaluated from 0 to pi thirds, and that will give us our j component. And then in the k component, we'll have minus 1/2 cosine of 2t. And again, evaluated from 0 to pi thirds. So now we need to evaluate these. The secant of pi thirds is 2. The secant of 0 is 1. 2 minus 1 is 1i. So in the I component, we just have 1. Let's see. The tangent of pi thirds is square root of 3. The tangent of 0 is 0. So in the j component, we have the square root of 3. And then finally, in the k component, I need to evaluate minus 1/2 cosine of 2 pi thirds, and then take away what happens when I plug in a 0. And we actually get 3/4. One of the nice things to do is to realize that this definition has really established what we could call the fundamental theorem of calculus for continuous vector functions, an evaluation theorem. If I'm taking the definite integral of a vector function, I can simply evaluate any of its antiderivatives from a to b. And so really this is no different than what we did way back in Calc 1 and Calc 2.